Exercise 18H, families of functions. A family of functions is one where one of the coefficients of a particular function is substituted with another pronumeral, usually an A or a B. And we need to just find a general understanding of what is happening to that particular set or family of functions. So unfortunately, these can get a little bit tricky because you have to have things in terms of A or B, but nonetheless, our previous understandings of solving for derivatives, making it equal 0 for stationary points is still applicable here. Example 1. Consider the function, that is the function f, that is unrestricted, is going for all real numbers, defined by f of x equals x minus ax squared, where a is a real number with a being greater than 0. The first thing we need to do is determine the intervals for which the derivative is positive and for which the derivative is negative. So we'll need to find the derivative, and then what we'll need to do is we'll need to find when it's greater than 0 and when it is less than 0. I would strongly recommend the drawing of a graph. So I found the derivative, and I've let that derivative equal to 0, and I've also gone and sketched the graph. How can this help me understand or solve the question? I know that a has to be greater than 0. So in other words, whatever this factor of a is, it's going to be a positive number. So therefore, I definitely know that the x-intercept of the derivative is going to be on the positive side of the x-axis. But why did I draw the graph of the derivative? If we remember from a previous video, anything that is above the x-axis on the derivative graph is a positive gradient. Anything that is below the x-axis on the derivative graph is a negative gradient of the original. So therefore, we can simply state here that for I, x has to be less than 1 over 2a, and for part 2, x is greater than 1 over 2a. You could have also solved this conventionally, since that's a linear equation, by doing some algebra. However, sometimes having the image there is very useful for us to see from a visual point of view. Part B, find the equation of the tangent to the graph of f at the point 1 over a, 0. So we're going to find the derivative. We're going to substitute x equals 1 over a, and then we're going to use that to find the tangent line accordingly. The tangent line will have some a's in it. The equation of the tangent line, I found I substituted the x value 1 over a into the derivative. So I put that into the derivative. That got me the value of m, which in this case is -1. And then what I did is I substituted this entire set of coordinates into the format y equals mx plus c, for that will tell me the gradient or the equation of a straight line being the tangent. And now for C, I need to find the normal to the graph of f. Thankfully, I've done most of the work for me. The normal is going to have an inverse, a negative inverse gradient to the tangent. So rather than having an m equals -1, it's going to have a graph, a gradient of y equals -1 over -1, which is equal to 1. Let's solve it accordingly. And now what we have done is we have found the equation of the normal, having since the gradient of the normal is 1, and we just substituted the coordinates 1 over a and 0 to solve for c, and then we get y is equal to x minus 1 over a. The last thing is to find what is the range of f. This one is a little bit more of a challenge to find, mainly because we have to understand what's happening with the graph. We know that a is a positive number. It has to be a positive number because we have established this here. If we look at the derivative graph that I've done, we know it starts going positive, then it has a turning point at 1 over 2a, and then it has and then the gradient is negative. So the original graph of y equals f of x is likely to look something like this. Where the x value of the turning point is 1 over 2a. But what we need to do is we need to find what that y value is, for that will tell us what the range is. So we just need to go and substitute that into the original equation. Having substituted the value of 1 over 2a into the original equation, I now have a y value of 1 over 2a minus 1 quarter. And so therefore that's the highest value of the graph, and therefore the range will be from negative infinity to 1 over 2a minus 1 quarter square bracket, because it's including. You could have also written this as y is less than or equal to 1 over 2a minus 1 quarter. Example 2. A line with equation y equals mx plus c is a tangent to the curve y equals x plus 4 all squared at a point P where x equals a, such that the x is somewhere in between negative 4 and 0. So we can see here, if we sketch a picture of this, there's our point P. And the point B is somewhere between negative 4 and 0. So well, I've just put it here for now. We can see that the curve here, this is the curve of x plus 4 squared. And so what we need to do is we will need to find as much as we can about this tangent line, quite presumably. At some point, we'll probably need to find this point P. Find the gradient of the curve where x equals a, for a is somewhere between negative 4 and 0. So we're going to do the derivative of that original function, y equals x plus 4 squared, and then substitute x for a. We have now found the derivative. I expanded the brackets so that we can do the derivative in a much easier fashion, and then substituted x equals a into that derivative, and I have the derivative of 2a plus 8. This means that the gradient of the tangent line at this point is going to be equal to that derivative. So hence, express m in terms of a, m is going to be 2a plus 8. In case you're getting confused, well, where is the a in the graph? Let's have a look back to this question. The point P is the value a, and it will have some coordinates here of a plus 4 squared. So that's where why we're doing x equals a, because that is the x coordinate of the point P. Well, and there we go. State the coordinates of the point P, expressing your answer in terms of a. I've just done that. I've predicted this question ahead of itself. We can leave it factorized. You could expand it if you like, but we may as well make it nice and neat. Now we need to find the equation of the tangent where x is equal to a. So we're going to need to use this derivative, this m value, and we'll need to substitute in the points a and a plus 4 squared to solve for c. So once I substituted m being the 2a plus 8 that we found earlier, then x is equal to a, because that's the x value of the point P. and I expanded the y value, that a plus 4 squared, because that will be the y value at the point P. I then substituted, rearranged into the tangent formula or the straight line formula, y equals mx plus c, and I generated this answer. For D, we need to find the x-intercept of this tangent, so we'll need to make this equal to 0 and solve for x. So I've now solved for x. However, I noticed that 16 minus a squared follows the rule of the difference of perfect squares, and I think I might be able to simplify this a little further. And now we have found the x-axis intercept by doing a simplification and putting it in coordinate form.